Bismillahirrahmanirrahim. This video is from chapter 6.4 of Mr. Sedra's book. Here we'll be discussing some theoretical aspects of amplifier design, and we'll also discuss example 6.13 and solve exercise 6.33. So some theoretical part. First of all, what is Q point? Q point is a point on the transfer characteristics curve or on the characteristics curve which is determined by the DC value of VCE, that is this voltage, and the DC value of the emitter voltage or the emitter battery. So this is called the Q point or operating point, or we can say the DC operating point. Now this graph you can see is divided into three parts. This part is the cutoff part. This is active part, and we'll be talking or operating in this mode actually. And beyond that, that is from here onward, is the saturation mode. Biasing enables us to obtain almost linear amplification from the BJT. So if you bias it properly, we can operate in this region which is almost linear. Now, three aspects I would highlight here. First of all, when the operating point is in the middle, then what will happen is that whatever is the input signal at the VBE, that signal will get amplified. And since it is in the middle, it will be equally amplified on both sides. Now, if this Q point is not in the middle, say it is here, up here, then what will happen to the same signal? Part of it will go beyond the cutoff point, so it will be out, and only this part will be visible or reproduced. And if we move this point, operating point, down, then what will happen? The negative half of the signal will be chopped off, and only this portion will be available. So it is very important that we understand the importance of the operating point or Q point. Now, the small signal voltage gain will be operating here, and one point I would like to emphasize, that this you can see is small v then capital VBE. That means this has actually two inputs. One is the DC, which is VBE all capital, and with that is AC, which is VBE all small, and the sum of the two is the small v capital VBE. Okay, now this we had seen, and you can see that if the slope is high, then we'll have proper amplification. The signal or the input signal will get properly amplified. But as the slope becomes low, like here, then we need a high input signal to get a almost similar output signal. So less amplification or no amplification in this case. So what we can conclude is that the amplification will depend on the slope of this line or the slope on this line. And so another way of looking at it, that this slope, which is actually dy by dt, we know, can also be written as dVCE. Now this is y VCE. So dVCE over dt is this line, which is VBE, so dVBE. The voltage gain of the amplifier will be written like this. The AV is dVCE over dVBE. Now we need to further analyze this dVBE and divided by dVCE divided by dVBE at this point where VBE is equal to VB capital E, that is at the DC point. Now VCE, from here you can see this VCE can be written as VCC minus ICRC, VCC minus ICRC. We have also learned in this chapter that IC is actually IS e raised to the power VBE over VT, where IS the saturation current. And if you put this value here, then the equation for VCE will be as shown here. Now this part is not linear, and therefore we can say that VCE is not linear unless we operate in the small region. Unless we operate in the small region, then we can get a linear output. Now putting this value of VCE in this equation, AV can be written as this. VC is constant, so this goes, and we're left with this. RC and IS we take out, again it's constant. So we'll have a D of this term. And if you see this e raised to the power EX, differential of e raised to the power EX can be written as A e raised to the power EX. So following same logic, here we get 1 over VT into e raised to the power VB VT, differentiating this part. And so we can write this, that RC divided by VT, and this is IS e raised to the power VBET. Now again, from here you can see that IS is actually equal to IC, and in this case we'll take IC as ICDC. So this is the final value of gain or AV. And equation 6.3 neatly writes this. So we'll be using this relation. Now we come to the example. This is the circuit. IS is given, RC is given, VCC is given, and we have to find these 4 parameters. We'll see them one by one. Now the first case, determine the value of the bias voltage VBE required to operate the transistor at VCE 3.2. So we have to find VBDC, actually this VBE, when VCE is 3.2. And also we have to find the corresponding value of IC. So to find VB, we will be using this relation. For this, we know IS is given, we know VT is 25 millivolt. We have to find VBE, and if we know IC, then we can easily find VBE. So let's try to find IC first from this relation. VCC minus VCE, which is known, 3.2 divided by RC. So 10 minus 3.2 divided by 6.8, 1 milliampere. So the collector current IC or IC-DC current is 1 milliampere. And now we'll plug in it here to get VBE. Now, typically IS is in the range of 10 raised to the power minus 12 to 10 raised to the power minus 18 ampere. But in example 6.1, it has been specified that NPN transistor IS is 10 raised to the power minus 15 ampere. So we'll be using this value here. So current was 1 milliampere, IS is 10 raised to the power minus 15. So from here we can get this relation, EVB over VT is this equal to, and we take natural log on both sides, then VBE VT will be Natural log of this part is 27.63. From here, VBE is 27.63 into VT, and VT is actually the voltage due to temperature, which is taken to be 25 millivolt. So when we plug in 25 millivolt, VBE is 690.8 millivolt. So this is the DC quotient voltage VBE. Next part, part B, is find the voltage gain AV at the bias point. And if the input sine wave is 5 millivolt peak amplitude is superimposed on VBE, find the amplitude of the output sine wave. First of all, let's concentrate on this. Find the voltage gain AV. This was the relation that we had found. And this can also be written as VCC minus VE divided by VT. You can see ICRC from here. ICRC is VCC minus VCE. Plugging in the values 10, 3.2 and 25 millivolt, the gain is minus 272 VB. But the minus sign actually means that when the input goes positive, the output will go negative. And when the input goes negative, the output will go positive. That means 180-degree phase shift. Okay, now we'll concentrate on the second part of the question. If the input sine wave signal is 5 millivolts, so here the input signal has 5 millivolt peak amplitude, is superimposed on VBE, find the amplitude of the output sine wave signal. So we actually need to find the amplitude of the amplified signal. And if you look here, this is 5 millivolt here, and we need to find amplitude of this part or this part. So the gain can also be written as V out peak divided by V in peak. And if the V in is 5 millivolt peak, then plugging in here, we can find the V out peak is 270 into 5 millivolt, that is 1.36 volt. There is no need of writing the sign. We just are concerned about the magnitude. Now let's see part C of the question. Find the positive increment in VBE that drives the transistor to the edge of saturation, where VCE is 0.3 volt. So a couple of things. We have to find the positive increment in VBE. That means here how much it is increased. That drives the transistor edge of saturation. So the output should come and touch the edge of saturation. So this is the saturation line. So it should be touching here. So initially the signal was like this, and now we have to increase VB so that this increases and touches this point. And one important point given is that VCE is 0.3. So this will be the last limit of the signal, 0.3. Now, at this point, VCE will be 0.3. We know this relation, so we have to find a new IC because VCE has now changed. Now for 0.3 volt, IC will be 1.617, 10 minus 3 divided by the load. Remember earlier IC was 1 milliampere. New IC is 1.617. So the current has increased, and that means VBE has increased. And to find that, we'll use a relation that we had discussed in one of the problems. So let me just summarize it here. The current IC is given by this equation. When IC is 1 milliampere like here, then we will write the equation with only change here that VB will be calling it VB1, and when IC is 1.6 milliampere, this VB will call VB2. And now if we divide this by this, then we'll have 1.617 at the top and 1 at the bottom, and IS will cancel. EVB2 over VT divided by EVB1 over VT. This can be written in this form, and VB2 minus VB1 is actually change in VB, that is delta VB. Now if you take log natural on both sides, then we'll get delta VB over VT is equal to log natural 1.617 over 1. Now this over VT, which was here, will come to the right hand side. VT we know is 25 millivolt, and multiply that with the log of this term, will answer is 12 millivolt. That means now the signal, which was input signal was this, will increase by about 12 millivolt. From here to here, the increase will be 12 millivolt. So this is part C. And similar is part D, but here we have to find the negative increment in VB. Now we'll increase this in the negative side, and when we increase VB in the negative side, then this will increase, the positive side will increase. That drives the transistor to within 1% of the cutoff. So 1% of the cutoff is actually this line. VCE is 0.99 of VC, and VC is 10, therefore VCE will be 9.9 in this case. So VCE 9.9, putting in here, we'll find another current, new current. This time the current is 0.0147, it has reduced. And following same technique, we have now one current 1 milliampere, the other current this one. And so following this relation, we get change in VE is to be minus 105.5. That means the negative side, it will now increase by minus 105.5 millivolt. So this was the question. And now let's see the exercise or the practice problem. Exercise 6.3. This also has three parts. We'll deal one by one. First of all, for the situation described in example 6.13, while keeping IC unchanged at 1 milliampere, find the value of RC that will result in a voltage gain of minus 320. So minus 320 will be the voltage gain. Current is given, so we can use the magnification relation. AV is equal to minus IC VT RC, and we have to find RC. IC is 1 milli, VT is 25, and AV is minus 320. So putting all the values, RC is 8 kilo ohm. So when RC is 8 kilo ohm, we can get the gain of minus 320. So this is the first part of the question. The second part is, what is the largest negative signal swing at the output? So output, the largest negative signal swing. Assume that VC is not to decrease below 0.3. So here also, this is the limit, 0.3. So let's see. First of all, we need to find the DC bias. So where we are operating, that we have to find. And the DC bias will come to be 2 volt, and let's see how it comes to 2 volt. We using this relation. Gain is given, VCC is given, VT is given, so VCE can be found. minus 320, all given, all given. So VCE is 2 volt. So that is how we get 2 volt here. And now from 2 volt, this could go up to 0.3. That means how much is the swing? 2 minus 0.3, that is 1.7. So VC swing is 1.7. Second part done. Third part, what approximately is the corresponding input signal amplitude? Now for all this, what will be the input signal when we have to reach this point? Now we have learned another formula for the gain, that is delta VCE over delta VBE. So we'll use that here. This is minus 320. Delta VCE we just found from previous slide is 1.7 for this. And then delta VBE can be calculated to be 5.3 millivolt. So change in VBE from old VBE to new VBE is 5.3 millivolt. So I hope you have been able to follow this. Thank you.